Hey, you calculus groupies. Today's lesson is on the antiderivative, and it is exactly what it sounds like. We know how to take derivatives. We know the power rule, the product rule, the quotient rule, the chain rule. We know implicit differentiation. We know all these different rules to get to a derivative from an original function. Now we're going to focus on going backwards, the antiderivative. So with that said, let's go ahead and get started with this. And like I said, the antiderivative is exactly what it sounds like. It's the opposite. It's the backwards to the derivative. So how do I go from f prime to get back to f is the purpose of what we're doing today. So let's go ahead and define some terms here. Normally we use the letter f to represent a function. You'll see in the lesson here that capital F is being used here. So we're going to say that capital F is the antiderivative to f of x. Okay? So here we have this notation that says if f of x is our function, then f prime of x is our derivative. Okay? All we're saying here is kind of the opposite. If instead of starting at f of x and taking the derivative, let's start at f of x and take the antiderivative. And we say, as a result of that, we say the antiderivative of f of x is capital F of x. That's just common notation. You can look at it this way. If I'm going to write a statement that would say that f of x, the derivative of f of x is f prime of x, and the derivative of f prime of x is f double prime of x, then we can add one extra line here and say that the antiderivative of little f of x is capital F of x. So it could just be tacked on to the sequence of derivatives. The derivative of capital F is little f, the derivative of little f is f prime, and then so on. So just to kind of get your head wrapped around that. As a result of that, you can see that if I take the derivative of capital F of x, that is equivalent to f of x. Okay, so that's what we're saying there. Now, let's go ahead and explore the idea of this capital F of x here. So if capital F of x is 2x to the third, if I'm going to go ahead and take the derivative of that, we would say that capital F prime of x, which is equal to f of x, is equal to 6x squared. Okay, so I think I have that in the lesson here. But just so we can see that, and notice I added that little statement there that helps us understand things there. Now, if I look at this other example, if I were to look at if capital F of x is equal to 2x cubed minus 1, if I were to take the derivative of that guy, that would be capital F prime of x, which equals f of x, is still equal to 6x squared. Now, hopefully that opens your eyes to this idea here that the difference between these two capital F of x functions is a constant. And if you remember, the derivative of a constant is 0. Now, if I did any constant here, so if capital F of x is equal to 2x cubed plus any constant, right? Any constant, when I go to take the derivative of that guy, the derivative of capital F, again, is f of x, is still equal to 6x squared. The point being is that capital F of x, if capital F of x is the antiderivative of little f of x, we have a problem here. Because all of these f of x functions are the same, but all of their antiderivatives are different. You can see that the antiderivative in this case is 2x cubed, but the antiderivative in this case is 2x cubed minus 1. The antiderivative in this case is 2x cubed plus any constant, really. So the point I'm trying to make is that capital F of x is not the antiderivative. It's an antiderivative. It's an expression, it's a function that relates all antiderivatives. And all of those antiderivatives differ by a singular constant. Okay? We can say all antiderivatives of a function differ by a constant. In other words, that there's a difference, they only differ by a shift, a vertical shift here. So let's go ahead and take a look at an example of what this looks like. Okay, So what is the equation that represents the antiderivative of f of x here? Now we know that f of x is equal to x plus 3. Now that's a pretty easy function to be looking at. We know that that's a line. And so we're trying to take the antiderivative of this. So just before we begin, we're kind of thinking through this. We're saying, okay, so since the function is a line and I'm trying to take the antiderivative, that implies that this is the derivative of the thing I'm trying to figure out. Well, if this is the derivative, if a line is a derivative, that means the function that produced that line as a derivative must be a parabola. Okay? So just kind of thinking through that logically a little bit. Now, going on and trying to figure out what this is, the antiderivative we're going to label as capital F of x. We're not going to go really deep into taking an antiderivative or how to take all antiderivatives right now. That will be reserved for second semester for the most part, but it's just an introduction. And mainly we're going to be talking about the power rule and how to undo the power rule in this lesson. So the first thing I note is that this guy is x. So then the antiderivative of this must be x squared, if that makes sense, right? Because again, if I take the derivative of this guy, I should get this. Well, if I take the derivative of this, I subtract 1 from that exponent, I get an x function there. Now, that still causes a problem for the coefficient, because if I were to take the derivative of x squared the way it is, the derivative of this would be 2x, and that's not what I have here. So what coefficient will counteract this 2 when I go ahead and multiply this in the front to make a coefficient of 1 here? And we would say that's going to be 1/2 of x squared. So, and then the last part, the plus 3, well, the antiderivative of that is going to be plus 3x. We'll spend some time in developing how to take that a little bit more efficiently. But for now, we just notice that if I take the derivative of capital F, if I take the derivative of capital F, so f prime of x, you remember that is lowercase f. So we should get this as a result of taking the derivative of this. And when I do take the derivative of that, 2 times 1/2 is 1, x, and then we subtract 1 there, so we just get x there. And the derivative of 3x is 3. So we in fact do get that function out when I take that derivative again. Okay, so we're trying to reverse the power rule here. Okay, now I'm going to throw in here this idea of adding a constant. And the reason we're adding the constant again is because this is not the only antiderivative to x plus 3. Because if I were to take the derivative of this constant is going to be, the derivative of the constant is going to be 0. So we don't really know what this constant is. We just know that it could be anything, really, any constant value. So with that said, let's go ahead and take a look at that graphically so we can understand the difference between these constants and the difference between the antiderivative here. If I said that f prime of x is 3x squared minus 2x plus 1, what is f? Well, we'll go through and explore this a little bit more in depth here. We know that f prime of x is equal to 3x squared minus 2x plus 1. And we are looking for f of x. So how do we go from f prime to f? We have to go backwards. We have to take the antiderivative. So before we do that, let me provide an example here of a derivative so we can see how this relates. If I were to say that g of x is equal to 7x to the 4th, for example, and I wanted to take the derivative of that, let's go ahead and go through the motions of that, but I want to go through step by step so we can see what's actually happening. Here, to take this derivative, we're just going to use the power rule. So remember, the power rule is, the first step is to multiply the exponent with the coefficient. So we would say 7 times 4, and then we would subtract 1 from our exponent here. So this would be x to the 4 minus 1. Now I know we can do all that in our head. We don't have to write all these steps out. But you're going to see how that relates if I go backwards. So the end result is 28x cubed. So we get that. But now we want to go from g prime back up to g. So let's go through the power rule, but we're going to reverse the idea. So remember, the first step in the power rule was to multiply the coefficient with the exponent, and the second step was to subtract 1 from the exponent. If I'm undoing that, I'm going to do the order backwards. So instead of the idea of multiplying first, I'm going to be dealing with this exponent first. So you know how we subtracted 1 to get to the derivative? We're going to go backwards. So to undo that subtraction, we're going to add 1. So we can say, just going backwards here, that g of x is going to equal something x to the 3 plus 1. So 3 plus 1 gets us back to the 4, so we can see that. Now the question is, how do we get rid of, or how do we deal with the coefficient? Well, going back up here, remember it was a result of multiplying the coefficient and the exponent, multiplying the coefficient and the exponent here. So to undo the multiplication, we're going to divide. The thing we have to be careful of, though, is that the number that we multiplied the coefficient by was the original exponent. So we did that before we subtracted. So down here, we needed to add so that when we go to undo it, we're going to be using the proper exponent. We don't want to use the 3 when we go to undo the multiplication. We want to use the 4. So to undo the multiplication, we're going to divide. So we're going to take our 28 and we're going to divide it by our original exponent. And our original exponent here would have been 4 because we added 1 to that. So simplifying this, we end up with g of x equals 7x to the 4th. And we can see that that's the same as what we started with here. So undoing the power rule. Undoing the power rule, just in summary, we're going to take our coefficient and we're going to divide it by the new power. Okay, so the first thing we need to do is add 1 to the power and then take our coefficient and divide it by the new power. Okay, so if we use that rule, and of course we would put plus c here, but we're just trying to compare it to g of x there. So if we undo the power rule here, first step is to add the exponent, add 1 to the exponent, and then we're going to take the coefficient and divide it by our new exponent. So it'd be 3 over 3. We're going to do the same thing here. We're going to add 1 to the exponent. So since the exponent's 1 there, this is going to be x squared. And we're going to take our coefficient and divide it by our new exponent. And then this guy, if you want, you could look at it this way. This is x to the 0. So we're going to take our exponent and add 1 to it. And we're going to take our coefficient and divide it by our new exponent. So as a result of this, and then at the very end, we have to put plus c, our constant. We're going to use a capital, I should probably emphasize that a little bit. We're going to use a capital letter C because it's not a specific constant, it's all constants. And you'll see that a little bit more in just a second. So go ahead and simplify this. We end up with f of x equals x cubed minus x squared plus x plus c. And so this is our antiderivative to f prime. Now, with that said, let's go ahead and make sure we're right. We always want to check our work by taking the derivative, and I can't emphasize that enough. In every problem, we want to try and work our way backwards from what we just did to see if we can get back to the original problem, just to check our work. We always make arithmetic mistakes, especially when we get to calculus. It seems like the algebra basics and the arithmetic disappear. You know, 2 plus 3, I get 6 all the time from that, right? Students give me 2 plus 3 is 6 all the time. So just be careful with that. So taking the derivative of this, x cubed would be 3x squared. The derivative of negative x squared is negative 2x. The derivative of x is 1. And then the derivative of this constant is going to be 0. So we did take the antiderivative correctly. So let's go ahead and take a look at a few other practice problems here. Might be a good idea for you to give these a shot before you watch the rest of this video. So for number 2, it says f prime of x is equal to x cubed over 4 and then plus 7x. Well, if I'm taking the antiderivative of this, I don't like this idea of a quotient. I don't know how to undo a quotient. So I'm going to rewrite this so that there's a coefficient out front. So the first thing I'm going to do is rewrite this as 1 over 4x cubed plus 7x. Now I can take that antiderivative easier. So the antiderivative of f prime is f. And so we're going to go ahead and add 1 to the exponent, so we get x to the 4th. And we're going to take our coefficient, which is 1/4, and we're going to divide it by our new exponent. So we're going to divide it by 4, if that makes sense, right? I'll put that in parentheses so we can see a little bit. Plus, now we're going to add 1 to this exponent, so it'd be x squared. We're going to take our coefficient and divide it by our new exponent. And then we've taken the antiderivative, now we're going to put plus c at the end. So simplifying this guy, we end up with 1 over 16 x to the 4th plus 7 over 2 x squared plus c. And that's our answer for number 2. Again, we always want to make sure that we're checking our work by taking the derivative of this to make sure we get what we started with. So the derivative of 1/16 x to the 4th, we multiply the 4 to the front, we'd end up with 1/4, and then x to the 3rd, that's this. And the derivative of this, we multiply the 2 to the coefficient, so that's just going to cancel out that denominator there. We're left with 7x, and then the derivative of c is just 0. Let's go ahead and take a look at number 3 here. Number 3 looks a little bit more complicated than it actually is. So f prime of x is equal to 1 over x squared. Okay, well, I want to go through and I want to take this antiderivative. Well, the first thing that I want to be very cautious of is that I see students do this all the time. They know this. They know that if f of x is equal to natural log of x, then the derivative of that is 1 over x. So they try and use this idea to solve this problem. Okay? The derivative of natural log of x is in fact 1 over x. And so they see some sort of connection here. The problem is that the exponent on this guy is 1. The denominator has an exponent of 1, where the denominator here has an exponent of 2. And so the natural log idea is not going to work for this case because the exponent on the bottom is not 1. And we're going to see more and more practice of that as time goes on. And again, we want to kind of double check our work. So I would get, maybe somebody would say f of x is just going to be the natural log of x squared, something like this, okay? Now, I want to check my work, so I'm going to go ahead and take the derivative of this guy to make sure it makes sense. So the derivative of this, remember the derivative of natural log is 1 over what's inside, so 1 over x squared. And then we have to use a chain rule in this particular problem, so it'll be times 2x, so the derivative inside. Now when I go to simplify this, we're going to end up with 2 over x here. Okay, so this is definitely not this. We have a problem. So the antiderivative of 1 over x squared does not have anything to do with the natural log. So if I look at this, well, considering I only know how to undo the power rule at this point in time, I'm going to rewrite this so that it looks like something that I can undo a power rule to. So I'm going to rewrite this as x to the negative second. So f prime of x is equal to x to the negative second. That's always a good idea when you're taking an antiderivative. If the exponent on the bottom is something other than 1, right? If the denominator has a variable with an exponent other than 1, it's probably a good idea to rewrite it with a negative exponent. Now I can go through and take the antiderivative of this. So I'm first going to add 1 to my exponent. So when I add 1 to negative 2, I end up with negative 1. And then I take my coefficient was 1, and I divide it by my new exponent, so negative 1. And then I'm going to add my constant to the end. So a result ends up being 1 divided by negative 1 is negative 1, and then x to the negative first plus c. Again, if I go to take that derivative to check to make sure I'm right, I multiply that, I end up with a positive 1, x to the negative second, plus 0, which is exactly this, which is equivalent to that. So that is my answer for number 3. For number 4, we have something that looks a little bit different than what we've been talking about. So we have f prime of x is dealing with a trig function. We have secant squared of x. F prime of x is equal to secant squared of x. I can't undo this using the power rule because the power rule requires that I'm raising a variable to a power. So I have to just kind of think through this a little bit. There is no specific rule that I'm using here. I'm just recalling that the derivative of a specific function is equal to secant squared, and that's just a recollection, that's a memorization thing. What function produces a derivative of secant squared x? And if you remember, you should remember, that tangent of x has a derivative of secant squared x. And then we're going to put the plus c at the end. So that's my answer for number 4. That's a pretty easy one if you have your trig functions memorized, if you have your derivative of trig functions memorized. Now number 5 is going back to what I talked about a minute ago. We got f prime of x is equal to 1 over x. Now the tendency here is to do exactly what we did in number 3. Rewrite this as a negative exponent. So if I rewrite this as a negative exponent, I would get x to the negative 1 power. Now we're going to have a problem with this if we try to undo the power rule here. If I try to undo the power rule, and I said f of x is equal to x to the, well, I'm going to add 1 to negative 1. I end up with 0. And then I'm going to take my coefficient, which is 1, and divide it by my new exponent, 0. Well, that's a problem altogether. Because if we're just going to look at the x to the 0, well, x to the 0 is 1. So we would end up with some sort of constant there. And if I take the derivative of a constant, I end up with 0, and this isn't 0. So that's wrong in and of itself. The other thing that makes this wrong is we're dividing by 0 here. So that's just a good indicator that this is not the appropriate way of doing this. So this is going back to the idea of the natural log. In the previous case, let me put that right next to it so that we can see this. If f prime of x was equal to 1 over x squared, we couldn't use natural log here because the exponent on the denominator was not 1. But here, the exponent on the denominator is 1. And so we know that natural log of x, the derivative of that is just 1 over x. So we would say natural log of x, and we're going to put an absolute value around this because the first reason it says that in number 5 it said that x is greater than 0. So we can't take the natural log of a negative number. So x is automatically greater than 0 in this case. But we do want to put an absolute value around here. Now, in other lessons, when we get into second semester and we go deeper into taking antiderivatives, we're going to see why a little bit more, why you have to put the absolute value there. But for now, just understand that we put the absolute value there because we can't take the natural log of a negative number. And then, of course, at the end here, we have to put plus c to represent our constant. So if I take the derivative of natural log of x, I get 1 over x. Derivative of constant is 0, so I know I did it right. So those are some great practice problems for just taking an antiderivative. Going on to the next idea now is trying to understand what this c thing does. And we've talked about it a little bit, but let's go a little bit deeper into this. But what about the c? What does the c mean? Well, let's go back to the idea that we had earlier where we had a linear function as our derivative. So let's say we were looking at the graph of a line. Okay, so this is the graph of f prime of x. Well, if I were to take this derivative, if I were to graph this derivative, I would note that for, how do I want to explain this? Let me put the graph up here a little bit so I can point to it. I've got the function that is decreasing. So it's just a line that's decreasing. And this equation is a pretty easy equation to see. Thinking of our chart, right, our relationship chart between our f and f prime, we know that this is our f prime graph, and we are looking for f graph, okay? We notice that f prime is positive for every x value less than 0. Well, if f prime is positive, we know that f is going to be increasing. So we know that this function is going to be going up. And then for every x value greater than 0, we see that f prime is negative. It's below the x-axis, which means the graph of f is going to be decreasing. So we're going to have a function that goes from increasing to decreasing. And again, just thinking through some ideas that we understand, The derivative, if the derivative is a line, that means the function must be a parabola of some sort. But let's go ahead and do this analytically here. The equation for this graph is just f prime of x equals negative x. Now when I go to take the antiderivative of that, we would end up with f of x equals, we're going to add 1 to the exponent, so that would be x squared. We're going to take our coefficient, which is negative 1, and divide it by our new exponent, so that's 2. And then we're going to add c to it. So this is our graph of our function. I'm sorry, that's the equation of f of x there. Okay. Now if I go to graph that, if I just leave it at the idea of negative 1/2 x squared, I'm going to end up with a parabola with an x-intercept of 0 and a y-intercept of 0. So the vertex is 0, 0. But c could be anything. So I could be looking at a parabola that is shifted up by some amount or shifted down by some amount. In each of these three cases, the only difference between these parabolas is the shift. And we can see that the plus c is a vertical shift. Okay? So that's what c represents there. It's just the vertical shift. These are all the possibilities of the f function if I know what f prime is. So that brings up the question, how do I know what c is? How do I know whether the parabola that I'm looking at is going to be somewhere up here or here or here? How do I know? In order for that to be known, we would have to have a little bit more information. So analytically, you would see that in order to find c, I would need to know every other unknown. If this is just a simple algebra problem, right? Simple algebraic equation. I would need to know what the y is and what the x is to know what the c is. So the point is, I would need to know a point on the graph. So if I were to tell you that this parabola, let me go ahead and erase this so I can point it out a little bit more here. If I were to tell you that this parabola passes through, let's say this point here, okay? That's going to give us some information about where the parabola is or what the vertical shift is here. I know that the parabola can't just be like this, where the c value is 0, because it would never hit that point. We would know that we'd have to shift up here to hit the point that I'm trying to get to. Okay? So analytically, what that looks like is taking the antiderivative, putting plus c, and then plugging in what we call maybe the initial condition to our equation to solve for that unknown. So let's go ahead and take a look at this example here. We know that f prime of x is equal to 2x plus 1 minus the cosine of x. So I want to take the antiderivative of this, so it's going to be f of x is equal to, the antiderivative of 2x is x squared, the antiderivative of 1 is x, and now here we're talking about antiderivatives, so I'm going to bring this idea up. A student of mine from years past came up with this little idea. They said if the derivative of sine of x is the cosine of x, and the derivative of cosine of x is negative sine of x, right? Then the derivative of negative sine of x would end up being negative cosine of x, because we have a constant negative 1. The derivative of sine is cosine. We put the negative out front. Now the derivative of negative cosine, well, ignore the negative. The derivative of cosine is negative sine. Now bring the negative back in. We end up back to positive sine. So this is the flow of a derivative. If I were to ask you what's the derivative of negative cosine, you'd say it's sine. The derivative of cosine is negative sine. But here we're taking the antiderivative. So that's why I put the arrows here, because the arrows imply taking derivatives. If I'm taking the antiderivative, I'm going to go backwards. So we notice here that we have negative cosine of x. So I want to take the antiderivative. So I'm going to go from negative cosine backwards. And so we see that the antiderivative of negative cosine is actually negative sine of x. And then we're going to put our plus c to represent that vertical shift. And again, we want to take the derivative of this to make sure it matches f prime here, and it does. Now, in this problem, it also gave us more information. It said that this function passes through the point 0, 3. Well, this is a y value. and this is an x value for the actual graph. So we're going to just take those points and plug it into x and y here to find c. So f of x is 3, plugging that in, equals, x is 0, so it's going to be 0 squared, plus 0, minus sine of 0, and then plus c. And then we'll simplify this so we end up with 3 equals, that all cancels out. The sine of 0 is just 0, so c equals 3 here. So as a result, we know our vertical shift. We know our graph, whatever this looks like, is going to have a vertical shift up 3. So our final answer is f of x equals x squared plus x minus sine of x and then plus 3. And I'm going to do this. I'm going to put parentheses around the x here so I know I'm not going to make a mistake in terms of what am I taking the sine of. I'm taking the sine of x, not the sine of x plus 3. So this is my final answer for that problem. Okay. Let's see here. So going through the motions again, take the antiderivative, then you go and plug the initial condition in to our x and y values to solve for c, and then we can rewrite the equation with actually knowing what c is. So here's a practice problem for you to give a try to. This graph, this function, we have f prime of x is equal to negative 1 over x squared, and it says for x is greater than 0, and it passes through the point 2, 1. So we need to find the function that passes through this point whose derivative is this. So remember we talked about this. The exponent in the denominator is not 1, so therefore the antiderivative of this function is not natural log of x. We're going to rewrite this as a negative exponent. So this is going to be negative x to the negative second. Then we'll take the antiderivative. So f of x is equal to x to the, we have to add 1 to the exponent, so that's x to the negative 1. We have to take our coefficient, which is negative 1, and divide it by our new exponent, which is negative 1. And then we'll add c at the end. So we end up with f of x is equal to just x to the negative first plus c. Or f of x is equal to 1 over x plus c as an answer there. With that said, we're going to take the derivative of this to make sure it matches this. In fact, it does, using the power rule. So now we need to actually figure out what c is. So we're going to take this coordinate and plug it into our x and y values. So we end up with 1 equals, let me rewrite that. 1 equals 1 over 2 plus c. So 1 equals 1/2 plus c. We're going to subtract 1/2 from both sides, so we end up with 1/2 equals c. So our final answer here is going to be f of x equals 1 over x plus 1/2. And there is our function. Okay. And then again, a quick recap. We rewrote this so that it's a power, and so we can undo the power rule. We took the antiderivative, put plus c at the end. We then plugged in our x and y values to find our c value, and then we rewrote the function with the actual c value in play. All right. One more slide to look at here, and that is a great example of applications of this idea. Okay, so we've talked about particle motion. We've talked about the idea that when velocity is positive, that you're moving in the positive direction. When velocity is negative, you're moving in the negative direction. When velocity is positive, that means our position graph is increasing, and vice versa. We know that we are at rest, the function is at rest, or the particle is at rest when velocity is 0. But now we're going to kind of go backwards with those ideas here, and this is kind of fun. It gives us, in this example, it says the acceleration of a particle is 4t. It tells us what the acceleration is. Acceleration is 4t. And if you're in a physics class, most of the time they only deal with acceleration being a constant value. But calculus allows us to go a little bit deeper into that idea where acceleration is variable, it changes. So acceleration is 4t. Its initial position is -2, and its initial velocity is -3. So this tells me the location at which the particle begins. So if if this is 0, if this is my origin, we know that we started at -2. We started in a negative position, and we know that the velocity is negative, so we know we're heading that way. We're heading back. And so we can, just a side note, since our position is negative and our velocity is negative, that implies that we're moving away from the origin here. Just a side note for other things that might be beneficial. But I'm going to go ahead and write this down. I'm going to interpret this in terms of coordinates. It says that our initial position is -2. That means that our position when t equals 0 is -2. Our initial position, initial implying that the time is 0. And we also know that our initial velocity is -3. So we know that v of 0 is -3. So that's some information that we know there. And it says, when is the particle moving toward the origin? When is the particle moving toward the origin? So how do we know when the particle is moving toward the origin? The particle is moving toward the origin when the particle is on the negative side of the origin and it's moving in the positive direction. So in other words, if the position is negative and the velocity is positive, I'm moving toward the origin. Or if my position is positive and my velocity is negative, I'm heading towards the origin. Either way, we have to figure out what our position function is and our velocity function in order to answer this question. So this is a pretty big problem here. So we need to figure out our position function and our velocity function given a of t. Well, we know that acceleration is the derivative of velocity. So we're going to say v of t is going to be the antiderivative of a of t. So the antiderivative of 4t is going to end up being 2t squared plus c. Now I can, right now I have enough information to figure out what c is because I know when time is 0, the velocity is -3. So I can go ahead and plug that in here. The velocity is -3 when the time is 0. So simplifying this, we end up with c equals -3. So my velocity function then is 2t squared minus 3. Now, like I said before, we need to figure out our position function from this. I'm going to go ahead and put that over here. The position function we'll call x of t. X of t is going to be the antiderivative of velocity. So the antiderivative of this guy is going to end up being t to the third, and then we take our coefficient and divide it by our new exponent. So it's 2/3 t to the third, and then minus 3t, and then plus another constant. So plus c. Again, this c value is not the same as this c value. We use the capital letter C to represent any and all constants. So we're not saying that this c is -3. If you want, call it d to represent a different variable. But now I know my initial position is -2 when t equals 0, so I can plug that in here. So I got -2 equals 2/3 times 0 cubed minus 3 times 0 plus c. Simplifying all that, we end up with c is -2. So our position function is 2/3 t to the third minus 3t minus 2. So that's my position function. I'm going to use that. And then my velocity function. Okay. So with that said, you're gonna look for when the position is positive and negative. You're gonna look for intervals for which the position is positive and negative. You're gonna look for intervals for which velocity is positive and negative. And if the signs are different here, wherever these signs of position and velocity are different, we know that we're moving towards the origin. I'm not gonna go ahead and solve that for now because that is something that we've done in the past. Just a quick reminder, you'd set that equal to 0, find the critical points there, and then do a number line and set up the positive and negatives. Do the same thing here, set this equal to 0, find those points where it equals 0, figure out where it's positive or negative, and compare the intervals for which the signs are different. This is going to require a calculator, and you're going to get some gross numbers for these guys. So probably be a good idea to practice it, but again, I'm not going to go over that today. I hope this is helpful in understanding the idea of an antiderivative. Again, an antiderivative is simply that. It's an antiderivative. It's not the antiderivative because you have that plus c there. So until next time, I'll see you around.